This week, as we get into measuring the behavior of gases, we talk about the ideal gas law, which is the expression PV equals nRT. And we've learned that P is short for pressure, and kilopascals or atmospheres, volumes in liters, and that temperature is always in kelvins. And we have this gas constant to help make the relationship between the pressure and the volume of a gas to its amount and its temperature, making that actual equation rather than a proportional relationship. But this N represents a thing called moles. So let's talk about what moles are so we can understand why we need to use them in chemistry. Moles is how we will combine on a macro level real substances or analyze the behavior of a particular substance. Like this week, we're analyzing how the behavior of gases by their pressure, the volume, the temperature, and by how much of that gas there is in a closed system. So we need to know what we mean by a mole. So a mole is a modern chemistry concept that has been devised to account for the fact that different substances have different weights. And so when we're trying to combine these in real world with a scale, we probably need to recognize the fact that a molecule of hydrogen is much lighter than a molecule of chlorine. Let's say we're going to make hydrogen chloride, better known when it's in water, dissolved in water, is hydrochloric acid. Now, hydrogen and chlorine are both diatomic. They occur in pairs in nature. We're going to kind of ignore that for today to make our point. Is that 1 gram, a little over 1 gram of hydrogen, according to your periodic table, 1.007 grams, is this number of molecules, a tremendous number, 6.02 times 10 to the 23rd molecules. That number is called Avogadro's number. We won't go into where that number came from. We're just going to accept the fact that that is a standard value. So on your periodic table that you have on your reference sheet and in your textbook, all those mass amounts known as the molar masses for each element in their little box is how much this number of atoms actually weighs. We can see why hydrogen is the lightest, because hydrogen is nothing but a proton and an electron surrounding it when it's in this elemental form. Chlorine, however, is 35 times the mass of hydrogen for the just one atom or the same collection number of atoms, because chlorine has 17 protons, 18 neutrons, and 17 electrons, a much, much bigger atom. It doesn't matter that this is 35 times heavier than this is. They both combine one atom to one atom, and thus we have to account for the fact if we're wanting to deal with real weights in real life instead of one atom of each and make a whole solution of hydrochloric acid, then we need to account for the fact of the disparity in weights for the same number of atoms that we hope will all combine. So at 1/35 the weight, hydrogen has the same number of atoms, and thus if we mistakenly tried to combine 1 gram of each or 20 grams of each, then that would be not very effective chemistry, because we're wasting a lot of material. In this case, we'd be wasting a lot of hydrogen, because we only need 1/35 the weight of this. So in other words, if I had 10 grams of hydrogen, then I need to multiply that 10 by 35 and make that 350 grams of chlorine to get the same number of atoms so that we can make the HCl. And so in the case if we're matching masses, this is bad, because 34 out of 35 of the weight, 34/35 of the weight of the hydrogen winds up being unused. We've wasted a bunch of material. So this is why we use the mole for very practical reasons. If we're going to be weighing out real amounts, to combine them, equal weights in most cases are not going to be effective. We're going to wind up having too much of one thing and not enough of another. Thus, we account for the weight disparity between these two. Now, in reality, we're never going to have perfect matching. We're not going to have all the atoms meet each other and combine into a compound or whatever new molecule. But it would make sense to us that a reasonable estimate of weight disparity is that for every one of our hydrogens, and as far as weight, we need to have 35 grams or kilograms of the chlorine. Because if the weight disparity is true on a micro level, it will be true on a macro level. Thus, Avogadro's number sets us to accounting for the fact that these substances weigh differently, and thus we can use the periodic table, which has worked out these different weights, to make sure that we have good, efficient chemistry happening, whether we're dealing with chemical reactions or dealing with the physical behavior of a gas.